This is Lecture 6, Bivariate Regression, Part 2. By the end of this lecture, you should be able to know how to run an ordinary least squares regression in STATA, know how to write a regression equation from regression output, know how to interpret the significance test for a coefficient in STATA, know how to interpret a significant coefficient for a continuous variable, know how to interpret a significant coefficient for a dummy variable, know how to interpret the significance test for a constant in STATA, know how to interpret a constant, know how to calculate predictions by hand and in STATA, know how to graph estimates in STATA, and know how to calculate and interpret an R-squared and adjusted R-squared. Before I move on to new material, I would like to review some material from the previous lecture. Recall that we begin the scientific process by identifying a dependent variable and an independent variable that we think has an effect on the dependent variable. We run a regression to determine whether the independent variable has a statistical impact on the dependent variable. The regression analysis produces in an equation dependent variable hat equals b hat times the independent variable plus a hat. B hat tells us the effect that the independent variable has on the dependent variable. If the independent variable has no discernible effect on the dependent variable, then b hat would equal 0. As the independent variable increases, the dependent variable stays the same. However, we expect the independent variable to have an effect on the dependent variable, so we don't expect the coefficient b hat to be 0. Based on our hypothesis, we expect it to be greater than 0 or less than 0. If we expect there to be a positive relationship between our independent and dependent variables, we expect that as the independent variable increases, the dependent variable increases. Hence, the coefficient b hat for this line should be greater than 0 or positive. If we expect there to be a negative relationship between our independent and dependent variables, we expect that as the independent variable increases, the dependent variable decreases. Hence, the coefficient b hat for this line should be less than 0 or negative. In the previous lecture, I showed you how to calculate an ordinary least squares regression by hand and conduct a significance test. Now I'm going to show you how to run a regression in STATA. It's really important for you to know how to run a regression in STATA and how to interpret the results, as you will be doing this throughout your graduate career. This slide tells you the steps you need to go through to run a regression. Let's say my independent variable is strength of upper chamber and my dependent variable is party's control over legislative candidate selection. I expect strength of upper chamber, the independent variable, to have a positive impact on the party's control over legislative candidate selection, the dependent variable. To determine if this is the case, I will run a regression. To run a regression in STATA, you type in reg, dependent variable name, independent variable name, and press enter. So I type reg, candidate select, strength of upper chamber into the command box here and press enter. The output should appear in this window. After you run your regression, this is what the results should look like. The first step in interpreting the results is writing your regression equation. I will show you how to do this based on this output. The first column here lists the independent variable name and the constant a hat. The second column lists the b hat, or the independent variable here, and the value of a hat here. In this case, b hat is 2.058028 and a hat is 3.180699. So if you recall, the equation for a regression output is dependent variable hat equals b hat times the independent variable plus a hat plus e hat. We are ignoring the e hat for the time being. So given that our dependent variable is party's control over legislative candidate selection, and strength of upper chamber is the independent variable, we have candidate selection hat equals 2.058028 times strength of upper chamber plus 3.180699. The next step in interpreting the regression output is determining if b hat and a hat are different from 0. We do this through interpreting the significance test in the regression output. I will start by showing you how to determine if b hat is different from 0. Recall from Lecture 5, the first thing you need to do when conducting a significance test is write your null hypothesis and alternative hypothesis. These are based on your original hypothesis. So based on our hypothesis regarding strength of upper chamber and party control over candidate selection, our null hypothesis should be as the strength of upper chamber changes, party control over legislative candidate selection stays the same, or H0 colon B hat is equal to 0. And since we expect a positive relationship between strength of upper chamber and party control over candidate selection, our alternative hypothesis should be, as the strength of upper chamber increases, party control over candidate selection should increase, or H1 colon B hat is greater than 0. So to determine if B hat is different from 0 in your STATA output, the first thing you need to do is look at the sign of B hat. If it is not in the expected direction, then B hat is not significant and it is indistinguishable from 0. So let's say you expected the independent variable to have a positive effect on the dependent variable, but B hat was negative. Then your B hat is automatically insignificant. You do not have support for your argument. If your B hat is in the right direction, then move to the next steps. Okay, so the next step is to look at the results of the significance test for the B hat in STATA. This column here, P is greater than T, tells you whether the B hat is different from 0. If this p-value here is less than 0.002, then the coefficient is significant and different from 0 at the 0.001 level. If not, move on to the next step. If the p-value is less than 0.02, then the coefficient is significant and different from 0 at the 0.01 level. If not, move on to the next step. If the p-value is less than 0.10, the coefficient is significant and different from 0 at the 0.05 level. If not, move on. If p is greater than 0.10, the coefficient is not significant and is indistinguishable from 0. In all of these cases here, you have support for your argument. The only difference between these three levels of significance is that here your results are significant at the 99.9% level. Here your results are significant at the 99% level. And here your results are significant at the 95% level. In Lecture 5, I only had you determine significance at the 95% level, but in academic articles, you are expected to demonstrate what level of significance you have. So I'm showing you how to do it here. Now, let's say your p-value is greater than 0.10. Once again, this means that your coefficient is not significant, and it is indistinguishable from 0. You do not have support for your hypothesis. An important note before I move on, anytime you see a p-value of 0.000, that is automatically less than 0.002, so you have significance at the 0.001 level. So applying this exercise to our regression example, I expected there to be a positive relationship between strength of upper chamber and parties candidate selection, or parties control over candidate selection. So first, I will look at B hat to see what the sign of B hat is. It is positive, which is what I expected. So now I move on to look at the p-value. The p is 0.000. Since it is less than 0.002, then the coefficient b hat is significant at the 0.001 level. Now let's say you have a significant coefficient. Congratulations, you have support for your hypothesis. You would state that there is a statistical relationship between your independent and dependent variables. You would indicate whether b hat was positive or negative, and you would say at what level it was significant at. Additionally, if the coefficient b hat were positive, you would say as the independent variable increases, the dependent variable increases. If the coefficient were negative, you would say as the independent variable increases, the dependent variable decreases. So following these steps for our example, we would write, the results of the data analysis suggest that there's a statistical relationship between strength of upper chamber and party control over candidate selection. The coefficient was positive and significant at the 0.001 level. As strength of upper chamber increases, party control over candidate selection increases. On the other hand, imagine your coefficient b hat were insignificant. Recall that b hat is insignificant when b hat is in the wrong direction or the p-value for b hat is greater than 0.10. You would say that the results from your analysis do not support your hypothesis. You cannot make any conclusions about the relationship between your independent and dependent variables. Now, there is a more sophisticated way to interpret significant coefficients. For independent variables that are continuous, meaning that the variable can take on 3 or more values, you can make a specific prediction about how the independent variable affects the dependent variable. You can say, as the independent variable increases by 1 unit, the dependent variable increases/decreases by the value of b hat. The dependent variable increases if the b hat is positive and decreases if b hat is negative. So using our example, we can say as the strength of the upper chamber increases by 1, party control over candidate selection increases by 2.058028. But what if we wanted to know by how much the dependent variable changed when the independent variable changed by half, or 0.5? We simply multiply the b hat by 0.5. 0.5 times 2.058028 is 1.029014. So we can say as the strength of the upper chamber increases by 0.5, party control over candidate selection increases by 1.029014. And what if we wanted to know by how much the dependent variable changed when the independent variable changed by 2? We can multiply the b hat times 2. 2 times 2.058028 is 4.116056. We can say as the strength of the upper chamber increases by 2, party control over candidate selection increases by 4.116056. Now, the previous slides apply to continuous variables. You have to interpret dummy variables a bit differently. Recall that dummy variables only take on 2 values, usually 0 and 1. In order to demonstrate how to interpret dummy variables, I will run a regression on the following hypothesis. Parties in countries with bicameral legislatures have more control over candidate selection than parties in countries with unicameral legislatures. In this hypothesis, party control over candidate selection is the dependent variable, and type of legislature, unicameral 0 versus bicameral 1, is the independent variable. Note that type of legislature is a dummy variable as it only has 2 categories. I'm going to regress type of legislature on candidate selection and in STATA. And here are the results. The coefficient for type of legislature is positive, and it is significant at the 0.001 level, so I can interpret it. The coefficient is 1.450011. So what does this mean? First, I must take into account that the data are divided into 2 groups, parties in unicameral legislatures and parties in bicameral legislatures. And the b hat is a comparison of the dependent variable between cases in the 1 category and cases in the 0 category. The B hat applies to cases in the 1 category, parties in bicameral legislatures, in comparison to parties in unicameral legislatures, the 0 category. I would say parties in countries with bicameral legislatures have 1.450011 units more control over candidate selection than parties in unicameral legislatures. Now I'm going to show you how to interpret a significance test for a constant in STATA. Recall from Lecture 5, we don't expect A hat to be positively or negatively different from 0. Instead, it could be either. So we interpret the significance test for A hat in STATA a little bit differently than we do for the significance test for B hat. Recall that the second row in your STATA output tells you the statistics associated with A hat. And this cell here tells you what A hat is. Is A hat different from 0? We will use the significance test to determine if it is. The P is greater than T column tells you the results of the significance test. Find out what the P value is and then compare it to these rules. If P is less than 0.001, then the constant is significant and different from 0 at the 0.001 level. If not, move on to the next step. If the P value is less than 0.01, then the constant is significant and different from 0 at the 0.01 level. If not, then move on. If P is less than 0.05, the constant is significant and different from 0 at the 0.05 level. If not, then the constant is not significant and is indistinguishable from 0. Also, note that anytime you see a p-value of 0.000, it is less than 0.001 and significant at the 0.001 level. Using the steps from the previous slide, when you interpret the constant, you say whether it is significant or not significant. If it is, you indicate at what level it is significant and whether it is positive or negative. So, applying this to our example, our p-value for A hat was 0.000. 0.000 is less than 0.001, so the constant is significant at the 0.001 level. And the constant is positive since it has a positive sign. So we would say that A hat is significant at the 0.001 level and positive. In addition, what A hat tells us is the value of the dependent variable when the independent variable is 0. So based on our regression equation, we could say when strength of upper chamber is 0, party control over candidate selection is 3.180699. This is a realistic prediction because strength of upper chamber can actually take on a value of 0. However, sometimes we have an independent variable that can't take on a value of 0. When that is the case, you cannot interpret the constant this way. So in the future, when interpreting your A hats, you will have to think about whether it is realistic to interpret them. Is a value of 0 for the independent variable realistic? So now moving on to some new material. In the next few slides, I'm going to show you how to calculate the estimates of the dependent variable for individual observations from your regression equation. Recall that the regression equation is the dependent variable hat equals B hat times the independent variable plus A hat. If you found that B hat was significant, then you can calculate estimates of the dependent variable for each individual observation. Otherwise, do not do it, as you don't expect your independent variable to have an effect on your dependent variable. So to calculate an estimate for an individual observation, you insert the value of the independent variable into your regression equation and calculate the answer. So recall our regression equation was candidate selection hat equals 2.058028 times strength of upper chamber plus 3.180699. So if for our first observation the strength of upper chamber was 0.67, then we would put a 0.67 here and do the math. So 2.058028 times 0.67 plus 3.180699 equals 4.55957776. You can calculate estimates for each observation in your data set. And if you did, the mean of the estimates would equal the mean of the dependent variable. Of course, it is easier to calculate estimates in STATA. First, you have to run your regression. Then you type in predict XB into the command box and press enter. And you should have a new variable called XB in your dataset. And you can graph these predictions. Click on the graphics option, click two-way, and create. Choose the plot type of your choice. I'm going to choose line. Choose XB for the Y option and the appropriate independent variable for the X option. So strength of upper chamber was the independent variable, so I'm going to select that. Click accept, click OK, and your graph should pop up. And remember, you can copy and paste your graph into a Word document. And you can also edit your graph. You should see Lecture 1 for a review on how to edit graphs if you want a review. I'm going to teach you about another statistic associated with regression. It is called the R-square. Recall that in regression, we expect variation in the independent variable to explain variation in the dependent variable. The R-square tells us how much the variation in the dependent variable is explained. The R-square ranges from 0 to 1. 1 means the regression equation perfectly estimates the dependent variable. 0 means the regression equation explains none of the variation in the dependent variable. This is the equation for the R-square. It is 1 minus the sum of the squared errors divided by the sum of the squared deviations from the mean. I will show you how to calculate this statistic in the next few slides using the strength of upper chamber, parties control over candidate selection regression. The first step in calculating the R-square is calculating the estimate errors. The errors are just the values of the dependent variable for a particular observation minus the estimate for that observation. So for the first observation, the actual value of candidate selection was 6. The estimate was 4.559578. So 6 minus 4.559578 is 1.440422. For the second observation, the actual value of candidate selection was 2. The estimate was 4.518417. So 2 minus 4.518417 is negative 2.518417. You would continue to do this for each observation. Recall that I had 987 observations in this data set. On a side note, after you calculate all of your errors, the mean of the errors should be 0. Next, we simply square the estimate errors. The error for the first observation was 1.440422. So 1.440422 squared is 2.074816. You would continue to do this for each observation. Then we sum the squared errors. Note that I did this for all 987 observations. I'm only showing you the first 4 here. The value was 2,895.367. Note that this value is the value of the numerator in the R-square equation. The next step is to subtract the mean of the dependent variable from each individual value of the dependent variable. So the mean of the dependent variable is 4.213779. So for this first observation here, the actual value of the dependent variable is 6. So 6 minus 4.213779 is 1.786221. And you would continue to do this for each observation. The next step is squaring the values from step 4. So for the first observation, we had 1.786221. 1.786221 squared is 3.190586. And you continue to do this for each observation. Next, we would sum the values from step 5. The sum of all 987 values from step 5 is 3,391.892. Note this is the value of the denominator in the r-squared equation. The next step is dividing the numerator by the denominator. 2,895.367 divided by 3,391.892 equals 0.8536. Then you subtract the value from step 7 from 1. 1 minus 0.8536 equals 0.1464. Next, you interpret the value from step 8. Our r-squared was 0.1464. We move the decimal place in the r-square over to the right twice and use it as a percentage. In this case, we would have 14.64%. Then we say that variation in our independent variable explains r-squared percentage variation in our dependent variable, or in this case, variation in strength in upper chamber explains 14.64% of the variation in party control over candidate selection. The adjusted r-square is another statistic you should be familiar with. It takes into account sample size and the number of the independent variables. The adjusted r-square equals 1 minus r-square times the number of observations minus 1 over the number of observations minus the number of independent variables minus 1. So applying this to our example, our r-squared is 0.1464. We have 987 observations and 1 independent variable. 1 minus 0.1464 times 987 minus 1 divided by 987 minus 1 minus 1 equals 1 minus 0.8536 times 986 divided by 985, which equals 1 minus 0.8536 times 1, which is 1 minus 0.8536, which equals 0.1464. So the adjusted r-square is 0.1464. To interpret this value, we move the decimal place over twice to the right and use it as a percentage. So in this case, we would have 14.64%. We say, after taking into account the number of observations and the number of independent variables, variation in our independent variable explains adjusted r-squared percentage variation in our dependent variable. So applying this to our example, we would say, after taking into account the number of observations and the number of independent variables, variation in strength in upper chamber explains 14.64% of the variation in party control over candidate selection. Obviously, calculating an r-square and adjusted r-square is a lot of work. So for the most part, you will be using STATA to calculate the r-square and adjusted r-square. The r-square and adjusted r-square are included in the regression output here and here. Now, the r-square is a general measure of how well a regression model estimates a dependent variable. Recall that when the r-square is close to 0, the regression equation does not estimate the dependent variable very well. And recall when the r-square is close to 1, the regression equation perfectly estimates the dependent variable. However, even if our r-square is high, which indicates that our independent variable is explaining a lot of the variation in our dependent variable, this does not mean our independent variable is consistently explaining variation in our dependent variable. It could mean that our independent variable explains variation in our dependent variable really well at lower levels of our independent variable and poorly at other levels of the independent variable. In addition, as you will learn in your graduate methods courses, there could be a variety of issues with your empirical models that lead to a high R-square, even though the model has problems. I've seen models with no significant independent variables with a high R-square. Therefore, I caution you in overvaluing the R-square. You will learn more about how to appropriately interpret an R-square in your graduate methods courses.